to have Matan Harel, who's joining us from Northeastern, from very cold Boston. And he's going to speak to us about planar percolation and the loop-ON model. Over to you.
Thank you so much for having me. I was telling Christina, I've been lurking this seminar for 5 years in the background, so it's awkward to be the person at the front, but I'm very excited to share this stuff with you. I'm going to be telling you about joint work I've been doing with Sasha Glasman, who's at Innsbruck, and Nathan Zalesko, who is my grad student here at Northeastern, about planar percolation and the loop-ON model. That conjunction is doing a lot of work. This is really sort of basically, what I'm going to be talking to you about is planar percolation on general graphs. Now, I feel like it would be an impossibility to try to describe everything that's known about two-dimensional percolation just because there is so much, like, under the last 25 years of percolation theory has been such massive strides forward in the study of planar percolation. But in most of the cases, for both historical and practical reasons, we're used to dealing with base geometry with a lot of symmetry. Lattices, and then if we want to move on from lattices to more mathematical things, Cayley graphs, quasi-transitive graphs, all these kind of objects where we have a lot of symmetry in the geometry. And that symmetry has a lot of consequences and ramifications for the percolation theory on it. These are sort of orthodoxies for percolation. I mean, the number of infinite components is almost surely finite, 0, 1, infinity, all these kind of things which we're very used to dealing with as sort of obvious starting spots. And I'm going to take all of that away. I am going to be saying, I am just giving you a general graph, completely general, and the one thing I'm going to keep is a topological, not a geometric condition, planarity. And that's going to screw up a lot of things. Sort of amazingly, it's not going to screw up everything. I'm still going to be able to say some statements. Specifically, there is a conjecture of Benjamini and Schramm from the paper in 1996, Percolation Beyond ZD, which is like one of those papers where they have like 10 conjectures. Each one of them is super interesting and has sort of birthed an entire field of study. One of their conjectures saying that like, as long as you're planar, you can sort of, 1/2 still has a special importance when it comes to Bernoulli percolation. That is Bernoulli percolation at 1/2. If it percolates, it must percolate with infinitely many components. And that's what I'm going to show. We'll sort of get into more details in a second, but the sort of story is a story of take away symmetry and what can you still say? That's the first half. The second half is the loop-ON model. The loop-ON model is a lattice model, the most symmetric object you can possibly hope for. I'm going to be talking about translation invariant Gibbs measure of that. And yet, I want to claim that this very general idea about percolation on general graphs is going to give me a lot of information on the loop-ON model, on this very symmetric object. And there is a bit of a trade-off where what thing you can do is you can take simple geometry with complicated correlations and translate it for simple correlations on complicated geometry. And that's sort of going to be the playoff. So that's the sort of 10,000-foot view of what I'm going to talk to you. But we might as well start with something, more concrete, such as what is percolation? So let's just start there. Oh God, I'm not scrolling. Scrolling, hooray. Great. So I'm going to be talking to you about site percolation. This is a solely site percolation. There will be very few bond percolation that you want to hear. And the setting is just going to be an infinite, locally finite connected graph. Here is one that I picked arbitrarily out of a hat. And a parameter p between 0 and 1. Bernoulli site percolation is a two coloring of the vertices. So I'm going to use 0 and 1, closed and open, etc., red and blue. And the Bernoulli site percolation is independent, where basically each of the sites is going to flip a coin, probability p make it blue or open, probability 1 minus p make it closed, flip a coin independently for its vertex, and we get a coloring. I'm going to call any two coloring of vertices a site percolation, but this is the Bernoulli one, and this is sort of the level of generality that I'm talking about. Now, the kind of questions we are interested in when we talk about percolation theory, as opposed to, let's say, random graph theory, is connectivity. So that's sort of the thing. I'm going to take two vertices and ask what's the probability they're connected, or more generally, what's the probability, I guess more specifically, what's the probability of finding an infinite component of one of the colors, specifically blue? Now, it is pretty straightforward that you can do a grand coupling of all of these Bernoulli percolations as p goes from 0 to 1, and in that coupling, as p increases, things get more blue. So in that generality, I'll make that sentence, as p increases, more sites open in the sense of the coupling. And from there, it's a hop, skip, and a jump to be able to define the notion of PC. So PC is just going to be the infimum of all p's, such that the probability that there exists an infinite connected component of open sites is positive. And we're going to take the infimum of that. The idea is that as p increases, things are 1. This set includes 1, it doesn't include 0, so you're going to have some set in between. But of course, PC could be equal to 1 and could be equal to 0. PC equals to 1 in the case of any one-dimensional graph. If you sort of take a tree which has 1 child and 2 and then 3 and then 4, etc., you get PC equals to 0. So in the level of generality that I'm giving you, this is sort of as far as we can get. Okay, I'm lying a bit. There is a bit more generality kind of things. First of all, the existence of an infinite component is a tail event. The Kolmogorov 0-1 law tells me that Bernoulli percolation is tail trivial, so I could translate that to equals 1 instead of positive probability. Once you have positive probability, everything is equal to 1. There is this recent work of Philippe Izzo, Vincent Tassion, and Franco Severo, which do actually, it's a slightly different notion of PC, but they do have, at this level of generality, a characterization for PC smaller than 1. There are things that can be said at this level of generality, but it gets hard to sort of, you can basically construct a graph that does pretty much any terrible thing you want if you think hard enough, if you just say an infinite graph. So as the title said, what I'm going to do is I'm going to basically restrict the rest of this talk to planar graphs. So basically, every time I talk about a graph, it's going to be planar. And what I mean by a planar graph is that there exists an embedding into the plane where no edges are crossing. This is sort of the standard combinatorial no K5 or K33 as minors. I'm going to assume very little else in terms of that when I talk about a general planar graph. Of course, we usually assume a lot more. So this is going to be a comically short little thing about percolation and vertex transitive graphs, but let's talk about percolation and vertex transitive graphs real fast. So what's a vertex transitive graph? Just a graph whose automorphism group acts transitively on the set of vertices. There is one orbit under the automorphism group. I'm also going to talk about quasi-transitive graphs where the number of orbits are finite. In more heuristic terms, all the vertices look the same, or there's only finitely many different types of vertices. That is transitive and quasi-transitive, respectively. I am going to focus on sort of the dumbest possible thing you can ask, which is just the number of infinite components for this thing. I'm not going to talk about more quantitative things just because that's unfortunately out of reach for most of this talk. So let's let n infinity be this number of components. And if I need to distinguish between the number of open and closed, it'll be n infinity in blue or red, sigma equals 1 or sigma equals 0. Anyone who's taken a percolation course will know that sort of one of the third or fourth things we say is on a transitive graph, n infinity is almost surely constant. That is, if I take a configuration and translate it in kind of thing, the number of infinite components doesn't change. And then because Bernoulli percolation is ergodic with respect to this translation, any translation invariant event is a tail event, is a 0-1 event. Therefore, these things are almost surely constant. And from there, hop, skip, and a jump, the only possibilities are 0, 1, or infinity. 0 and infinity are sort of Kolmogorov 0-1 kind of statements. They're really just like, you can't change them with finitely many components. 1 is a lot trickier, but it does work by translation invariance. And then if you have any number more than 1, you can just sort of take a big ball, intersect it, and open all the vertices on the inside, and get that if you have 15 components, you can also have 1 component with positive probability, which is a contradiction with almost zero finiteness. So already the assumption of symmetry simplifies the possible statistics of n infinity to almost surely constant in one of these 3 things for any value of p. Now we're going to get into a bit of geometry. Amenability is going to have to come up. What's an amenable graph? An amenable graph is just when you sort of take larger and larger sets, there exist sets that exhaust the graph whose boundaries are small. So think lattices, think anything which has Euclidean geometry, anything which has polynomial growth, anything like that, and some things that have exponential growth as well, so that depending on how you design them, I have some way to exhaust the graph so that the boundary is relatively small versus volume. The sort of amazing, and still every time I think about it, I love this theorem more, the Burton-Keane argument, tells me that on such things, only 0 and 1 are possible. I can comment a lot more on the Burton-Keane question because it's one of those things where a lot of work has been done in sort of distilling it down to its base, and there's still more to be done there, and I still have some interesting questions on sort of what generality Burton-Keane works in. But it is fundamentally a geometric argument. It is fundamentally something where I'm giving you some information on a transitive graph's geometry, and I'm getting something out of n infinity. It also brings up the sort of really obvious question of, is this an if and only if? In the sense of, if a graph is non-amenable, do we always have an infinity phase? Just to sort of be concrete about this, Here is a particular non-amenable graph. This is the four regular tree or the Cayley graph of the free group on the free product of groups on two, a free group on two generators. That's what I meant to say. Just this lovely little thing here. And it turns out, I guess Russ Lyon did this in the 90s, I think, for any tree. We can understand this graph sort of by hand using hierarchical structure. And PC of this graph, of a general d-regular graph, is 1 over d minus 1. So in the case of this is a four regular tree, PC is 1/3. And if I take a particular coloring of, let's say, 1/2, just to keep things symmetric, what we get is infinite components. But we get a whole lot of them. We get basically every vertex can sort of birth in its direction with a positive probability once you're above 1 in D. And in fact, you've got infinitely many of blue and infinitely many of red, as long as P is between 1/3 and 2/3. And you do have this kind of phase transition in that direction. As I mentioned, the obvious question becomes for a general non-amenable graph or non-amenable Cayley graph, non-amenable Cayley graph or generally vertex transitive, is it true that non-amenability implies that there is an n equals infinity phase? As far as I know, that's still wide open in pretty much every case. Let me just state it a bit more clearly. There is this notion of PU. So if PC is the appearance of an infinite component, PU is the first P where you have a unique infinite component with positive probability. The conjecture is that for every quasi-transitive graph, PC is equal PU. That is, we go from 0 to 1 immediately, if and only if G is amenable. This is the beginning of a story. So we also have things like the Hagstrom-Paris theorem, which tells you that, like, for a general graph, as you sort of increase P, you go from 0 to infinity to 1 in that order. For vertex transitive graphs, you have some really interesting construction by Schoenmann, for example, which sort of introduce a couple of other critical parameters, Px, the sort of the largest P where you have uniform exponential decay in all difference in the things, Pcon, the infimum of all P where you have two vertices that are arbitrarily far away that connect to one another with positive probability. There is so much more to go into here in sort of understanding on just the vertex transitive side. But what I want to tell you is that I want to break all of these things. So let's see what happens when I sort of move away from transitive graphs to general planar graphs. Here's a general planar graph. The upper half plane is the triangular lattice, the lower half plane is the triangular lattice, and I have exactly two edges connecting them. Now, pardon me for waving my hands a bit. For this graph, if P is smaller than or equal to 1/2, there are no infinite components. This is well known by sort of monotonicity and the fact that the PC of the triangular lattice is equal to 1/2. But if P is larger than 1/2, we actually have an infinite component in the upper half plane and another infinite component and an infinite component in the lower half plane. If we just restrict to that thing, that is sort of a known thing about half plane percolation. But are they the same component? The answer is maybe. In this picture, they're not, because you can sort of see that the little land bridge that I have is blocked over here, but it could be that this vertex would turn blue and maybe it connects there. So already we have a situation where n infinity can be 1 or 2 and is not almost surely constant. Okay, you may say, okay, Matan, this is silly. This is a two-ended graph. There's an infinity on top and an infinity at the bottom, and you sort of connecting the two things. Of course that you're going to have something quite like, you can't expect this to not work out. Fair enough. Let me try again. Now imagine taking those two slits and putting one vertex, then two vertices, then three vertices as they sort of go along in each direction. And this is now one-ended. Topologically, there is no question that you can get from each way to each way the thing. But Bernoulli tells me that the number of monochromatic things, if I look at the number of edges going left to right, which are genuinely monochromatic, am I not connected to the electricity? I'm sorry, I need to check something for a second. I am not. Oh, Lord. Sorry about that. My computer was making alarmed noises. Apologies. By Bernoulli, if we look at the number of monochromatic edges of monochromatic passes over here, there will be finite. So even though this is now one-ended, we still have an infinite component at the top and an infinite component at the bottom, even though this is perfectly one-ended. And of course, I could do pretty much whatever I want inside those slits. Take your favorite planar graph. If you can embed it in the plane, you can probably embed it in this little slit with some terrible infinities and accumulation points. Stick it in there, connect it there, you've got another planar graph. What happens? It's really unclear. It's really not, there is nothing sufficiently obvious from the topological constraint as to how an infinity should act here. At this point, I will want to say, you might be asking me questions about embeddings, because as you can sort of tell, this is a bad embedding. I have to sort of make these circles smaller, and you can imagine as I go further, those circles are going to get really, really small. And I don't know if most of you are probably familiar with the notion of circle packings, which is somehow the correct embedding, which somehow conforms to the conformal structure theoretically. It's a discretization of the conformal structure one expects for these graphs. I am going to take the radical position of not caring. I fundamentally do not care how you're going to embed a planar graph. And this was sort of one of the big breakthroughs we had in studying this thing, is to basically abandon geometry completely. And I'm going to be speaking almost purely topologically here. I am going to give you an embedding. That embedding is going to have accumulation points at certain points. And I think all I know is that edges don't cross. It is planar. And that's it. So I am not particularly interested in how these things, and this is in certain ways fighting with one hand behind my back, because the correct embedding can give me a lot of structure. On the other hand, it's going to sort of clarify the things that can happen by just saying, I don't know, I have this big black blocks and just some kind of a curves in space that are going to be used there. So this is one thing that can go wrong. N infinity might not be almost surely constant. Here's another thing that can go wrong. Let's take my same triangular lattice at the bottom, and at the top, I'm going to attach a tree. This particular tree is periodic. It goes 1, then 2, then 1, then 2, then 1, then 2. Its branching number is 1 over root 2, is square root of 2, excuse me. And now let's consider colorings of this graph. So at the bottom, I've got a graph whose PC is 1/2. At the top, I've got a graph whose PC is 1 over root 2. And that means that the phase diagram looks like this. From 0 to 1/2, nothing. From 1/2 to 1 over root 2, a unique infinite component. From 1 over root 2 to 1, infinitely many infinite components. So goodbye, Hagstrom Paris. We don't have that anymore. Even worse, this graph is amenable. If you take large enough basically sets inside the square and then slowly but surely crawl up the tree, you will get Fellner sets. But we still have infinitely many components between 1 over root 2 and 1. So that nice little piece of orthodoxy doesn't quite work. And this is the questions I have about Burton-Keene and sort of what happens there as well related to this, but I'll leave that to another. But both of these graphs do have the same PC, 1/2, right? We got this triangular lattice part. I could change that by making the branching of the top part higher. But if I do so, I'm doing so by making things that are sort of locally not amenable, whatever the hell that means. Fundamentally, what I need to do is I need to introduce a hyperbolic geometry to this graph, a very hyperbolic geometry to this graph, in order to push PC smaller than 1/2. If you want to think of the sort of the geometry that's being discretized by a very, very, very high degree tree, it is one that splits, it has exponential growth. It's one that sort of looks not flat. It has negative curvature look. And this was sort of the fundamental question that Benjamini and Schramm asked in 96. They said, can you do anything else? And in fact, they conjectured you cannot. For any locally finite connected planar graph, Bernoulli percolation at 1/2 can do one of two things. It can either not percolate, or it must have infinitely many components. So we proved this result, and we in fact proved something slightly stronger. So let me actually give you the result that Sasha, Nathan, and I proved. So I'm going to let G be a locally finite connected planar graph. And sigma is going to be a generic site percolation with 3 properties. The first is tail triviality, so the Kolmogorov 0-1 law. Just tail events must have probability 0 and 1. The second is very important, and that's positive association, the FKG inequality. Very heuristically, the idea is that increasing events make other increasing events more likely. And this is sort of a big gun, admittedly. And well, I'll discuss this a lot because I have very strong love-hate relationship with the FKG inequality. And the third is a stochastic domination condition. I want the set of blue vertices to be stochastically dominated by the set of red vertices. Now, any percolation process that has these three properties on a planar graph satisfies the Benjamini-Schramm conjecture. That is, either you have no infinite components or infinitely many infinite components of the smaller color. So this is for sigma equals 1. Sigma equals 1 is always the smaller or equal color. So let me make a couple of comments here. First of all, I'm assuming literally nothing about G except planarity. No symmetry. It can be a complete monster. Nothing about its accumulation point structure. So even there is, this is actually a quasi-transitive graph, but it's a really interesting one. If you take the square lattice Z2 and take the free product of it with a group of two generators, so basically you have a Z2, and above each vertex you got a Z2, and above each of the vertex you get a Z2, you get this incredibly large, very branching graph. Believe it or not, that graph is planar. Still blows my mind. It satisfies, you can sort of prove this combinatorially. Any embedding of it in the plane will have basically a Cantor set of accumulation points, and yet this theorem still holds. So this can hold for some really, really ugly objects out there, because we really don't care about how the embedding works at all. We really just expect it, just deal with it on that level. The other thing is that I never really talked about Bernoulli percolation. I assume no independence. I only assume tail triviality, positive association, and stochastic domination. One of the most tantalizing things that I'll hopefully have some time to speak of at the end is we can apply this to things like super level lines of the GFF, for example, which are FKG naturally. And a lot of questions about, let's say, recurrence and transience of planar graphs all of a sudden come in play using the connection of the GFF and the random walks, especially with the recent work of Pete Lammers, which sort of tells you percolation properties versus delocalization properties being related to one another. So there is some really interesting stuff that we'll explore, and hopefully I'll have time to talk about it at the end. I will note, tail triviality, of course, for Bernoulli percolation with p smaller than or equal to 1/2 falls under this category. Tail triviality is the Kolmogorov 0-1 law. Positive association is Harris's inequality. And Bernoulli P versus Bernoulli 1 minus P, whichever one is smaller than or equal to the other works. And it in fact works all the way to 1/2, not just strictly smaller than 1/2. So the result that we're going to get is that actually at 1/2, either you don't percolate or have infinitely many components. I do want to sort of talk really quickly about the sort of most obvious question, which is, okay, cool, what does this mean about PC? One of the things this tells me for planar graphs is the question of, do things percolate at 1/2 now translate to, can you rule out an infinity equals infinity? Can you rule out the coexistence of infinitely many infinite components at 1/2? So this, or for general P, even better, but for 1/2 would be sufficient. Now, Burton-Keane basically already tell us this. If my graph is amenable and quasi-transitive, I'm done. PC of the family of such graphs is larger or equal to 1/2. This was actually proven slightly before us by Grimmett and Lee in, I want to say, 2023. So this was known before our work, but it was a slightly more hands-on kind of thing that really required a lot more. They had to work pretty hard to move it to quasi-transitive. There is another class of graphs we can talk about, which are the unimodular graphs. So unimodular graphs are not transitive in the sense where every vertex can look different, but they are families of rooted random graphs where they are sort of, I think of them as statistically vertex transitive. That is, if you, the roots can be anywhere equally in an equally likely fashion. So they sort of inherit a lot of the properties of transitive graphs, even though they're not transitive, they're using the rerouting operation that they have to commute with in the sense of mass transport. Now, this was known a lot before us. I want to say this basically goes back to Aldous and Lyons, that basically everything you want to do in terms of Burton-Keane kind of things work for unimodular random graphs. So here's a corollary. Let G be a graph that is the limit of finite planar graphs in the sense of Benjamini and Schramm. Equivalently, this graph is planar, unimodular, and invariantly amenable. This is just a notion of amenability which sort of plays nice with the rerouting operation. PC is larger than 1/2. We rule out the possibility of n equals infinity, and then our previous theorem just magically, you're done, and then the only other option is 0. So this is the kind of thing that the zero infinity law can tell you, all the way to 1/2 for Bernoulli percolation. The only thing that can go wrong is infinitely many infinite components. So that's already pretty nice. Just like, as far as I know, this is new. I don't think anyone else has actually managed to prove this without any additional assumptions. I do want to talk about a few other works that were sort of done before us about this kind of thing. And the two major ones are done for node symmetry, but with a minimal degree condition 7. So the idea of the minimal degree condition 7 is that if you have a minimal degree condition 7, the circle packing is somehow uniformly negative curvature. Just think of the triangular lattice, everything has degree 6 and everything packs nicely in the plane. If you want to make the degrees be 7, you sort of have to twist plane to make things fit. So you get this kind of uniformly hyperbolic, uniform negative curvature kind of condition using the circle packing. So if you have that and this notion of a well-separated embedding that is no accumulation points in some embedding, then you can get things like, actually, we do percolate at 1/2. So PC is strictly smaller than 1/2. And this is Hausgrave and Panagiotis. Hope I pronounced Christophorus' name correctly. So that's one condition. Basically, this is enough to show that we are squarely in the hyperbolic side of this equation. It is way too strict. This is not the correct condition, but it is definitely a sufficient condition. And the other thing is this inequality PU is larger or equal to 1 minus PC, which Zhongyan Li proved 2 years ago. The way I think about this inequality is that basically it's not a no coexistence result, so the kind of thing where you can't have infinite components of both colors simultaneously. It's in fact a if coexistence, then a lot of coexistence. If you have infinite components of both red and blue at the same time, they both must be infinite. I believe this is true in general. The first statement can't be true in general. We know we have planar graphs with PC larger than 1/2, the square lattice will do. But the second inequality, that PU is always larger than 1 minus PC, should be true for all planar graphs. We're currently working on it, but this is more of a technical thing that needs to be made. On a different direction, and this is sort of outside of the fact that it's the work that inspired this work to begin with, it's also a very different kind of result. Ron Pellet in 2020 proved a uniform P star such that if you look at any P smaller than P star, what you get is exponential decay of correlations, of connectivity. The big asterisk here is that this is not a graph distance statement. This is an R2 statement. The distance is measured in R2, and you must use the circle packing. So if you have a circle packing that essentially lives in a disk, this is sort of the standard Schramm thing for triangulations, this is empty because, you can't make it after a certain distance. And what does it matter if exponential decay if there are no vertices after distance 1? So that's pretty silly. But for all other graphs, this can actually give you this kind of condition. The unfortunate thing about it is that it's perturbative. This P star is really small. I think we got to like 1/10⁴ or something like that. It's not good, but it is uniform. And this was actually quite instrumental in some of the other work. And the question of the reason I mention this is because it brings up the very, very big question of quantitative results. I have none of them at this point. And the question of interacting with the way that this works outside of just n infinity, is it there or is it not, you're going to need some level of geometry. There's my topological approach is probably not going to work. So this was what I wanted to tell you about complete generality. I do want to talk about 2 applications before I go back and try to prove this to you, depending on time. The first is one that probably I'm not sure if too many people are familiar, and this is the so-called divide and color models. So divide and color models are given in the I think they were first studied by Hagström, if I'm not mistaken. The way it was done initially was what you did is Bernoulli bond percolation on the lattice, and then took each connected component of that and assigned it a color of the vertices independently. So the idea of a divide and color model in general is take your favorite graph, partition it in some random way, and then do uniform colorings on those partitions. That's what I'm going to call a divide and color model. So here's a particular version of divide and color. I'm going to take my triangular lattice and I'm going to divide it into partition classes. And I'm going to insist that each one of the classes is finite. I don't care anything about it. I'm insisting that each one of these pieces only has finitely many vertices in it, and it's translation invariant. So take your lattice, do this kind of thing, and then color each one independently. Blah, da, da, da. Keep going. Do that. That gives me a 2 color with vertices. It's a side percolation. And then I forget about the vertices and just look at the coloring that's generated by this. And this is where things started getting interesting for me. If anyone has talked to me about percolation in the last 5 years or so, you probably heard this screed already, so I apologize. I have been spending several years trying to write a course, which I'm going to call the FKG inequality and its discontents, with apologies to Sigmund Freud, because this is an incredibly useful tool, which is too easy to break. It is silly how much we can't do the second we don't have the FKG inequality. There are some very, very straightforward questions I do not know how to answer, or at least don't have a good answer for. We'll deal with this later. But this result, the theorem I gave you, had positive association as one of its assumptions. However, divide and color is not necessarily FKG. if you just take a graph on, let's say, n vertices, and imagine that you partition it into all the vertices but one, and then all the vertices but the other one with probability 1/2, the probability that like two vertices are red is going to be not, did I get that right? No, the probability that everything is, sorry, I get confused. This is a very simple example. No, I apologize. Take half the vertices and then a bunch of singletons versus half the vertices and then a bunch of singletons. The probability that everything is red is going to be the number of classes to the 1/2, but each of the vertices, each of the probabilities will be essentially a quarter, because there's a probability that everything is there and then that vertex is 1/2. I overcomplicated this. Fundamentally, as an annealed law, divide and color is not necessarily FKG. As a quenched law, it is. If I tell you the partition classes, this is nothing more than Bernoulli percolation. So what I'm going to do is I'm going to apply my theorem to the quenched law. Given omega, this is a side curve for a fixed omega. This is an FKG tail trivial because everything is finite. And therefore, omega almost surely, the number of infinite components is either 0 or infinity. Based on the translation invariant, I can run a Burton-Keen style argument on this, a sort of unimodular version of the Burton-Keen argument, and rule out infinity. And then omega almost surely this does not percolate, which means this divide and color model cannot percolate. So any two coloring that I can express as a divide and color model with finite classes that are translation invariant, so there are several stipulations, automatically does not percolate with no need to actually have positive association. This is where we sort of move into the lattice model picture here, because it turns out that there are some very complicated and very weird, nicely symmetric objects which can be written in terms of these divide and color models, have divide and color type representations. The one I want to talk to you about is the loop ON model. So let me sort of do a very quick job of trying to describe what the loop ON model is in that way. So the loop ON model is naturally defined in the hexagonal lattice, and it is a model of interfaces. So if I take this piece of the hexagonal lattice over here, I'm going to call a subgraph a loop configuration if every vertex has even degree. What does that mean? I got loops. Because every vertex has degree 3, two loops can't intersect with a single vertex. I'm cheating using the hexagonal lattice. And the only thing that can happen is a bunch of closed loops or by infinite paths in the infinite case, but let's not worry about that for right now. So I have a loop configuration is just what it sounds like. Given two parameters n and x, I'm going to sample a loop configuration as n to the number of loops times x to the number of edges, normalized in the standard way. So I have 1, 2, 3, 4, 5 loops here, however many edges, that'll be the weight of this configuration. We'll look at all possible loop configurations to give me the partition function, and we sort of normalize that way. So this is what I'm going to define as the loop ON model with two parameters n and x. Intuitively, the larger x is, the more edges that I want. The larger n is, the more I want to split n up into small little pieces. One of the main issues with the loop ON model is making that intuition into formal math is fundamentally impossible. We don't have any nice monotonicities, or at least any direct monotonicity in this kind of thing. The idea is that you increase x, sure, you're giving things more weight, but what about the entropic repulsion of having loops not intersect? How do you actually understand the interplay between these two things? And the answer is that, at least directly, you don't. This is one of the things that makes studying the loop ON challenging. Of course, there are ways around it. Now, that's the hard side. And the reason on the sort of the good side is that the loop ON model has many, many things of interest as special cases. I'm only going to talk about two just for the sake of time. But let me sort of talk about the first and most obvious one, which is interfaces can be thought of as domain walls. So if this is the interface, I can just take a face, color it blue, and then every time I cross a line, I change colors from blue to red, and then I cross a line, I go from red to blue, etc., and go to that. And basically, this is a 2-to-1 mapping, excuse me. It's once I determine the color of one face, all the other faces are determined, and I get basically a spin model on the faces, a two-coloring, a site percolation on the faces, according to my definition, whose interfaces are exactly going to be the loop ON configurations, the loop configuration omega. I have a law here, I can push forward the law over here. So I can formally write this law as just a function of these colorings. In general, the law is complicated. If n equals 1, however, the number of loop terms just drops out completely, and what we only get is a nearest neighbor model. What nearest neighbor model? This is just the Ising model. So if I just set n equals 1, and I get that the loop O1 model is just the domain walls or low temperature expansion of the Ising model on the triangular lattice with x is equal e to the minus 2 beta. So if x is smaller than or equal to 1, this is a ferromagnetic Ising model. If x is larger than 1, this is an anti-ferromagnetic Ising model with a negative beta, if you'd like. But it's really sort of as nice as it gets. This relation does make sense for any general n, but it has long-range interactions if n is different from 1. But we can write, that's one thing that's sort of well-known, and we're going to take advantage of later. Another thing which I think might be less known and I want to sort of advertise is if we take just the triangular lattice, the domain of the triangular lattice, put zeros on all the boundaries and assign integers to every face. So we have a map from every face to integers such that the difference between any two things is 0 or plus or minus 1. Here's a particular instantiation of that. Just to make it a bit easier to read, I'm just basically considering this is integer valued Lipschitz functions of the triangular lattice. It's one Lipschitz. The difference between any two things is 0 or 1 or minus 1, depending on what it is. And what am I going to look at here? The only thing I really can, the interfaces, that is the gradient lines. So let's consider the lines that separate things that have a difference of plus or minus 1. And then let's forget about the numbers and just look at the marginal on the interfaces. How many different ways can I assign integers to this? Well, every one of these loops goes up or down. The weight is 2 to the number of loops. This is the loop O2 model. So integer valued Lipschitz function is the same as the loop O2 model, where x tells you whether you locally want to favor a gradient or not. X smaller than 1, you do not favor a gradient. X equal x larger than 1, you do favor a gradient. So you get something very similar to that. There's also interesting things to like dilute pots if n is a square root of an integer. So root 2, root 3, root 4, root 5, etc. in all the direction. I'll be brief for the sake of there's no way I'm going to get done with everything I want to do in 20 minutes, but we'll see how far I get anyway. What does the loop ON model look like? So here are, I'm worried that you can't see this well, so I'm going to try to describe it. Unfortunately, the coloring didn't quite work. Here is a sample that I actually simulated, well, Inon Spinken simulated, and I stole his simulation at n equals 1.4 and x equals 0.6. The colors here don't mean anything. They're just trying to visually emphasize the 1, 2, 3, 4, 5 longest loops. Oh, sorry, not to give away the punchline. What we see here is there's a couple of large loops, but mostly we have a relatively empty space, a lot of very short loops, a few ones that are a bit larger, but not a lot of nesting either. Here's the same thing at x equals 0.63. So I changed x by a very small amount, and I hope you will agree with me that at least qualitatively, this is a very different looking picture. The long loops are a lot longer. They are nested inside each other. The interfaces are complicated. There are some small loops. There always are. They have a finite energy kind of argument to say that you can always insert a small loop. But we see this geometry is a lot more convoluted. What we're seeing here is a subcritical phase to the left, where what we expect is exponential decay of lengths. That is, if I look at a particular vertex and look at the statistics of the loop that goes through it, it should have exponential decaying behavior, and basically every face should be surrounded by finitely many loops, and basically we have some level of exponential decay. On the right, what we're seeing is a conformally invariant phase. This is going to have infinite nesting. It's going to sort of, the scaling limit should be a CLE ensemble and all these kind of things. This is a fractal picture. When we move from 0.6 to 0.63, it is a phase transition, of course. Nienhuis in 82 sort of introduced this model as an object analysis non-rigorously, made the following conjecture, which is super tantalizing. We have this curve, xc is 1 over the square root of 2 plus the square root of 2 minus n, because of course it is. What else would it be? You have this particular curve right here. Thank you. I'm glad at least it's really hard to do this, that sound. I'm like, I think this is one of those things that's sort of funny to sort of course, this is the only equation that could come up. But it is actually a very logical thing when he compared this to the Potts model in a very non-rigorous way. To the left of it, we see an exponential decay phase. To the right of it, we see an entire phase of conformal invariance. So if we look at the geometry, for any value of x larger than xc, we expect a conformally invariant behavior. And also on the critical line xc, we expect a conformally invariant behavior. The other surprise is that when n is larger than 2, we expect no conformally invariant behavior whatsoever. So we actually have something special happening at n equals 2, where the line actually goes all the way to the right. This is actually sharpened later with the advent of CLE and SLE and all these things to say that what we actually expect is two conformally invariant phases. On the line XC, we expect one SLE, one CLE behavior. If X is larger than C, we expect a different CLE, with the exception of n equals 2, which of course gives you CLE4 and everything's a GFF and everything's the same on the entire critical line. So the and just in case you're wondering, here are the formulas of these Ks, these kappas, just in case you're curious. It's more, what's important to me is that you get something different on the line than off the line. We're very, very far away from this. I don't think it will surprise anyone in this room to say we know conformal invariance at exactly two spots. N equals 1, X equals 1, because N equals 1, X equals 1 is a uniform coloring of the faces that is Bernoulli percolation on the triangular lattice. It is the interface of Bernoulli percolation on the triangular lattice, famously has the conformally invariant limit is known. The other is X equals 1, sorry, N equals 1, X equals 1 over root 3. This is critical easing, the other place where these things are known. On those 3 points, the work of Stas Smirnov, etc., forgive me for not giving the bibliography appropriately, we do know conformal invariance in both of these points. I'm going to ask for something a lot more modest. I'm just going to ask for evidence of conformal behavior. And there are sort of two different phases, two different ways to do this. The first is a so-called Russo-Seymour-Welsh RSW regime. The idea here is that basically if I take any annulus in space and give any boundary conditions on both the inside and the outside, and I look at sort of a hexagon of size n and another hexagon of size 2 and around it, inside there I could find a loop of configuration or not find a loop of configuration with positive probability. This is so-called Russo-Seymour-Welsh estimates. These are tortuosity, fractality estimates, tortuosity estimates, precompactness estimates. These are sort of the gold standard of saying this thing, if a limit exists, it will be fractal and look like the kind of CLE thing that we're looking for. So that's the sort of the strong, I'm going to call that macroscopic loops, loops of every scale fractality. The other weaker version is what I'm going to call long loops, which is just saying if I look at any face, there are infinitely many loops that surround it. So infinite nesting with nothing quantitative to go with it. As you will notice, the lack of quantitative is a theme, unfortunately, of this work, because when we zoom out as much as we do, we sort of lose a lot of the details in terms of more quantitative results, but that's what we call long loops. Now, what am I doing? I can pretty much in one slide tell you everything we know rigorously about the loop ON. So here is everything that I believe is known. I'm putting a thing. In red, I have the two spots that I mentioned of conformal invariance. In purple is this notion of macroscopic loops. We get this on the line over here. This is just subcritical easing. N equals 1, X between 1 over root 3 and 1, subcritical ferromagnetic easing. We have this critical line over here, this point down here, and the line N equals 2, X between 1 over root 2 and 1. Just to give the credit where credit's due, this is classical results of subcritical easing. This is Hugo-Dominic-Kopan and Smirnov. This on the critical line between 1 and 2 is Dominic-Kopan, Peled, Glasman, and Spinka. This is Lammers and Glasman to get this line here. And the N equals 2, they use the association with the Lipschitz functions to be able to sort of say more than we were able before. And this is what makes N equals 2 special, N equals 1 special. The blue regions are places where all we have is long loops. And this is my work joined with Nick Crawford, Ron Peled, and Sasha Glasman, where we were able to sort of extend it a bit to the ferromagnetic easing and extend it in this. This is a bad picture because this is really a 1 minus epsilon and 1 plus epsilon. It was a very much a perturbative argument initially, which we took just around this corner and we're just like, we got positive Lebesgue measure. We got something that actually fills space and not just something that on a particular line where something magical happens. So what we can do now is take that square and make it as big as we can. We can actually extend that square all the way to this point, 1 over root 2, comma 2, which is in many ways a critical point. This is the largest possible square we can possibly fit in this thing, and we get long loops on that entire regime. And additionally, if we have nx squared smaller or equal to 1, we can actually upgrade that to macroscopic loops. Now, what is this nx squared equals to 1? It turns out that with nx squared is smaller than or equal to 1, and x is smaller than 1 and n is larger than 1, so sort of this region in this parabola over here, the two-color representation that I mentioned before, where we just sort of pick a color of a face and then flip it every time we see an interface, it's positively associated if and only if nx squared is smaller than 1, excuse me. So Our argument does not use that. It's just an a posteriori. What that tells us is that under these FKG kind of regimes, we have these dichotomy theorems, which basically tells you exponential decay or macroscopic loops, nothing else can happen. These are the kind of theorems that were initially leveraged by, say, Domenico Pantacion and Sidor Vicius to sort of analyze a lot of the FK models, but these is really general FKG kind of phenomenons where basically you're either subcritical or supercritical and nothing, or critical, excuse me, and none of these intermediate behaviors can be done. The actual theorem we proved is really this blue square to just say, without FKG, without really any good representations, all we can say is we must have long loops. We must have this infinite nesting. And that's really the thing I want to focus on. Now, how do we do this? I'm going to do my best to try to convince you that this is really nothing more than a divide and color question. The inspiration for this is essentially the Edwards-Sokal coupling. For those of you who don't know, if I take any graph, there is this bond percolation thing system called FK easing, where one thing I can do is I can take an FK easing system, which is just going to give me some percolation system, and then given a configuration of FK easing, each of the edges can represent a constraint on the model that the spins on the two opposite sides of the vertices have to be the same. So when I give you a FK easing configuration, I can color them such that every single connected component of FK easing must have the same color, and every components which are not connected have independent colorings. And if I look at that, what I get is the easing model exactly. The idea here is that I can sort of come up with a geometric expansion, a random set, that the entire correlation structure of easing is encoded by the fact of whether things are connected or disconnected in this thing. And I can sort of do that by sort of, okay, once I have these components, I color each one of them independently. A divide and color model, exactly as I described before. I claim that loop ON is also a divide and color model, although it's slightly more elaborate. So let me sort of give you the idea of how we do that. I start with a loop configuration. I'm going to construct what I'm going to call defect vertices. So first of all, every loop I'm going to call a red defect loop with probability n minus 1 over n. Notice n minus 1 over n when n is between 1 and 2 is a number between 1 and 1/2. What I'm going to do next is I'm going to thin the lattice by 1/2. So I'm going to consider all the so-called y vertices. So these are these vertices right here, which are sort of forming a y as opposed to a, I don't know, Mercedes-Benz symbol. So this is the kind of all of these vertices over here. And there are vertices on the loops which are already red. And then every vertex that's off the loop is going to flip a coin and be red with probability 1 minus x squared. Why n minus 1 over n and 1 minus x squared? Because that's how that's the thing I need to do to make the partition functions work out. I promise you I'm not cheating here. This is just a way of expanding essentially like n is equal to n minus 1 plus 1 to the number of loops and sort of just doing some binomial style expansion there. There's nothing hidden over here. Now, I now have a bunch of red vertices and a bunch of black vertices. And these y vertices sort of can be connected. If I connect each y vertex to all of its neighbors, I get a triangular lattice of these y vertices, right? Each one has degree 6, and you sort of connect there. And then I'm going to just forget about the black vertices and look at connected components of red in this lattice. So like this vertex and this vertex and this vertex and all these, and this one all form one component. This is a different component because you have to make it fair. So let's look at the marginal on just the defect vertices. This is a divide and color model. If every loop is finite and n minus 1 over n is smaller than 1/2 and 1 minus x squared is smaller than 1/2, so x is between 1 over root 2 and 1 and n is between 1 and 2, this doesn't percolate because this is a planar graph and I don't need to tell you anything else. I don't care how large these loops are. I don't care what terrible geometry. I don't care if they loop onto each other and have nesting. Don't care. As long as they're finite, my abstract result tells me these do not percolate. Great. Now I take that Edwards-Sokal kind of perspective. What Edwards-Sokal tells me is that each one of the edges forces spins to be the same. If I follow here, what this tells me, every defect forces all of the faces that border it to be the same. So if I sort of, what I do is I basically stick a triangle on each one of these vertices. And look at the connectivity here. Guess what? Same thing. The infinite components of these triangles is the same as the infinite components of the red, and these two must be finite. Now, How do I get to a loop configuration? What I do is I color the faces along each of these components. So all of these are red, all of these are blue. Flip a coin on each one of these. What do we have? A second divide and color model. Because using the first application, I know each one of these components is finite. And then I can apply my theorem, everything is finite. I can apply it again and get a coloring here. And under this coloring, every component of blue and red must be finite as well. What does that mean? Well, let's look at the interface. I start here. At some point, this blue component is going to be finite, so I'm going to switch to red and have a thing surround me. Then this red is going to somehow switch to blue, surround me, and I have infinitely many loops that surround me going all the way around. So fundamentally, there is no chance of getting something quantitative or something this silly, but if all you want to get is just there is a loop and another loop and another loop and another loop, these divide and colors are actually sufficient to get me there. So this is sort of the story of how we use this rather innocent looking divide and color to deal with this very complicated by way of the correct geometric representation. Should give credit. This was sort of a combination of Edward Sokol and Newman did this expansion in N when x equals 1 before that, and then Nick, Ron, Sasha, and I combined the two for the paper, which did asymptotically, and then we sort of massaged the details a bit to do it right the second time and get this optimal result that we got right here. I've got like 5 minutes. Something like that.
Yeah, you can have a little bit longer than 5 minutes.
Thank you. Appreciate it. So what I want to do now in the sort of 8 minutes, and this is going to be a bit of a rush, and I'll hopefully not speak too quickly, is I want to go back and sort of tell you how things work for that planar percolation result. And the inspiration for this is a very famous sort of result, again, one of those textbook results, which is Zheng's argument for no coexistence of the triangle lattice. So as a warm-up, I want to tell you a little bit about Zheng's argument for showing no percolation at 1/2 for the triangular lattice. The statement is if p is equal to 1/2, neither blue nor red can percolate because they have, in fact, the same statistic. Let's see how that works. It's an argument by contradiction. Let's assume that blue percolates. By tail triviality, if I take k large enough, if I take a sort of diamond in the triangular lattice and make k really, really big, it will hit the infinite component. Since the infinite component exists with probability 1, I can take k large enough so that the probability that it does not hit the blue infinite component is at most an epsilon. I think that's pretty safe. Now, what does this event say? Left side does not connect to infinity, and top side does not connect to infinity, and right side does not connect to infinity, and bottom side does not connect to infinity. By the FKG inequality, these are decreasing events, but the FKG inequality works for decreasing events. I can say that this is smaller than the product of all 4 of these probabilities. And then, this is the triangular lattice, they're as symmetric as they possibly can. This is just the probability that this one side does not connect to infinity outside the box to the 4th power. So that tells me what this is the so-called square root trick. The idea is that basically this localized tells me that with incredibly high probability, this top side will connect to infinity in blue. Make that epsilon be, I don't know, I think 1/256 is going to do just a small number, you'll see in a second. So if I take the 4th power of each side, I get like a 1/16 is the upper bound on that probability when k is large enough. Now, where at peak was 1/2, so the probability that blue connects is the same as the probability that red connects. And then by union bound, I claim that the probability that all 4 of these things connect, that is the left side by red, the right side by red, the top by blue, and the bottom by blue, all 4 of these must happen with probability 1 minus 4 epsilon to the quarter, because the complement of this event is at least one of them does not connect, 4 times epsilon to the quarter. So this is sort of the initial insight. And then we say the following. Let's look at the inside. Usually, so if you open a Grimmett's textbook, for example, they'll say, well, by finite energy, you can paint everything inside blue, and therefore we have a positive probability of having 2 infinite components in red, and therefore that kind of thing. I want to do this slightly differently and just say, I don't care what coloring you choose on the inside. By pure planar topology, either top is separated from bottom in blue, or left is separated from right in red. One of these things has to separate. There's just no way to connect these things simultaneously. So this event implies that there are at least 2 open components, or at least 2 closed components, infinite components or that is blue and red. So this is by another union bound. The probability that n infinity of blue is larger or equal to 2 is at least 1/2 of this. That's a positive number as long as epsilon is, what is it? Whatever 1/4 to the 4th power, something slightly larger than that will do. This is a positive number. Ergodicity tells me that we have infinitely many components almost surely. But of course, this is the triangular lattice. The triangular lattice cannot hold infinitely many components as an amenable quasi-transitive graph. Therefore, contradiction. What I'd like to emphasize here is that there's actually 2 steps to Zeng's argument. There is start with an infinite component and then split it into 2, and then say, no, you couldn't split it into 2 because you have uniqueness. These are 2 ontologically distinct kind of parts of the argument. But we do use basically 2 parts that are very strong. We use symmetry over here, and we use ergodicity. The question becomes, can I do it without both? The answer is yes, but I'll try to convince you that that works out. So let's just do a quick recollection. What is it that I actually want to prove to you? I want to prove to you that if I have tail triviality, positive association, and stochastic domination, this works out. For the sake of simplicity and the fact that I've got like 3 minutes, I'm going to replace stochastic domination by just p equals 1/2, so red and blue have the same law. And I'm going to assume that the planar graph has a good embedding so that I don't have to worry about accumulation points or anything like that. Okay. Let's try this. I'm going to assume I have an infinite component, and I'm going to say, okay, this graph is a mess. I don't know anything about its structure, but I know by measurability that if I take a large enough thing, it'll hit the infinite component with good probability. So if I take some Jordan curve, which only goes through the vertices, which I can find because there's like uncountably many such objects, so you can always avoid edges and things like that, I will find some terrible Jordan curve that connects to infinity with really good probability 1 minus epsilon. Putting our topologist hat on, this is a circle. It's not a circle. It is some terrible shape, but topologically speaking, it is a circle. And the probability that this circle connects to infinity is very, very big. 1 minus epsilon at least. What I want to do is I want to split it into 2. And I want to split it into 2 components, each of which connects to infinity with really good probability. This is just to give, again, to give credit where credit's due. Vincent Tassion, many, many years ago, when we were both postdocs in Geneva, told me the sentence that's been sort of bouncing around my head for years, which is, sometimes it's important to let the probability do the geometry for you. And this is exactly what we're going to do. I know nothing about this curve. What I'm going to do is I'm going to crawl along this curve, and I'm going to keep adding vertices until I get this probability to be decently large. And I'm going to hope that the other probability is going to stay large. So fundamentally, I'm going to define J to be the final time where the probability of not connecting here is larger than epsilon over 2. That is sort of, if I add J plus 1, I connect all the way to infinity with probability at least 1 minus square root of epsilon over 2. I'm rushing through this. That automatically, by just an FKG argument, tells me that this guy connects with probability at least 1 minus square root of 2 epsilon. And this guy could be small. But I'm only adding 1 vertex. How much can that 1 vertex help when I know with probability 1/2 that vertex is red? So even though I don't know that this probability is large, it can't be that much smaller. The probability that 1 to j connects to infinity might be small. It can't be that much smaller than the probability of adding j plus 1. So forgive me for flashing through this really quickly, but fundamentally, when you sort of follow this with FKG, we can split this up by saying, okay, just keep adding vertices, no regard to geometry, until you find an arc that connects to infinity with good probability. And both of these things, you go from an epsilon to a square root of 2 epsilon, but you can do this arbitrarily many times. Do it twice, do it k times, I don't care. Pick an epsilon large enough and say, I take this thing and split it into k arcs, each one connects to infinity with good probability. And then by the sort of union bound kind of thing, they all connect to infinity simultaneously. Well, why not switch colors? This is not a geometric statement. I'm going to go along this terrible Jordan curve and say, this is a landing site from blue. This huge thing is a landing site from red. This tiny thing is a landing site from blue. I don't know, but each one of them connects to infinity with good probability because that's how I constructed it. Now, I claim that for any coloring of the inside, maybe there is only 1 red component. Maybe there's only 1 blue component in all the red split. The sum of the 2, if there are k alternating arms here, the sum of the number of infinite components of blue and the number of infinite components of red has to be k plus 1. I'm flashing this really quickly. This is the reason. This is sort of a Catalan argument where if you want to connect this guy to this guy, you automatically separate this guy from this guy. And you sort of have these places where if you switch, if I connect blue instead, I have to separate red. This is a fundamentally planar topology statement. There is nothing geometric happening here. I know zero information. In fact, I don't even use planar duality in the sort of traditional sense of star connectivity versus usual connectivity. This is just how things work in the plane. So the sum of these things has to be large. And basically, that means that with good probability, at least one of them is at least k plus 1 over 2. By symmetry, at least one of them has uniformly positive probability. This is independent of k. So taking the intersection over all k, we show the probability that there is infinitely many components is positive, and then Kolmogorov's 0-1 law tells me that, in fact, I have infinitely many components with probability. That was really fast. I do apologize, but I'm looking at the time kind of thing, and I do want to very, very briefly tell you about a few things that still remained open. The most obvious question is, okay, which is it as 1/2? If I just give you a graph, does it percolate or does it not percolate at 1/2? And as always, Itai Benjamini gives me the obviously interesting and really, really difficult conjecture, which is if I have a graph G, it's planar, it has uniform degrees, and its dual has uniform degrees. That is, it's a triangulation or a quadrangulation. There is sort of a total bound. Then percolation happens at 1/2 if and only if you're transient. That is, the correct thing to look at is the random walk. And this somewhat makes sense in the sense of sort of like, is it hyperbolic? Is there a place which is hyperbolic? And the random walk will capture that, because if there is sort of a part of your graph which is hyperbolic in certain senses, the random walk will use that and be transient, and that will give you a PC that's smaller than 1/2. I will tell you the number of times I've tried and thought I had something here once you realize that it was patently wrong, and that you actually, because you do need both of these assumptions. There are perfectly nice bounded G with perfectly locally finite G stars where this is wrong, as long as you don't have the uniform bound. This is, I have to say, we're really, really far, just a really nice conjecture that's still open, and somehow that 1996 paper will never be solved, I feel, at least not in my lifetime. But, so that's one question that I want to make sure I advertise. The other is this PU minus is larger or equal to 1 minus PC. That is, if we have coexistence, we have hard coexistence, infinitely many components of both colors is the only way both colors can percolate. This one feels a lot more manageable. We're working on it right now, but it's more of a technical issue than a sort of deeply conceptual one, I feel. The other thing is, again, questions of random walks. This is a place where just there's the very famous result of Benjamini and Schramm in 2001, which proved that Benjamini-Schramm limits of uniformly bounded degree planar graphs are recurrent. This uses circle packings. It uses a so-called magic lemma. It's a beautiful piece of work, but it has some heavy machinery packed into it. I believe Omer Angel and Tom Hutchcroft have a result that uses circle packing, but no magic lemma. We can do this now with none of them using the technology that we have here, and Pete Lammers' argument on delocalization and percolation connection for integer valued random functions, or real valued random functions, random height functions as well. We're trying right now to figure out, can we do Asaf Nienhuis and Oleg Algorevich's version, which drops the uniform bound degree for exponential bounds. But we got stuck in some really weird things here, because it turns out that I don't even know just a planar unimodular invariantly immune graph. It's not clear that all of those are recurrent. In fact, they're not. You can do some weird situations where you actually have a pair of dual graphs on a surface where one is transient and one is recurrent. So there are, and this is a weird example because you end up having things like PC equals 1 for these graphs, and like random walks are they're recurrent in very, very weak senses and transient in very weak senses. So it's weird examples, but even getting the correct condition here is interesting. And very finally, this was recent work by myself, Michael Eisenman, Jacob Shapiro, and Owen Pellet. We sort of use this kind of stuff to talk about the BKT phase transition. Can we do this on more general geometries, planar geometries? Because we really needed lattices before, but it seems like this opens up a lot more there. Sorry, I did go a bit long, but thank you guys very much for sticking around with me.
Matan, thank you very much for a very stimulating talk. Can I invite, has anybody got any questions? Maybe just some quick ones. I'm aware that people will want to go off and have their cups of tea. I think I've got silence there, and in the interest of wrapping up, I think I maybe will hold back on asking you anything, but do feel free to get in touch with Matan if anybody has any questions.
Absolutely.
Thank you so much for joining us. I'm going to stop recording and